we are going to go back over chapter number 5. We're going to do number 6. We're going to run through the whole thing because when you get to A and B and C, those are what we did yesterday. Those are relatively easy, right? But when you get to D, I need you to kind of go through it. It's not a complicated math problem. In fact, it's actually really easy, but setting it up from scratch can be confusing. So we're going to kind of just start from the beginning and do this one kind of just all the way through. They tell us that the river is 400 meters wide. Okay, we have a boat that's traveling at 15 meters per second across, but we also have the river that's traveling south at 7 meters per second. The question is, if you were to stand on the side of the river and watch the boat kind of go down, then how fast is the boat actually moving? If you combine the river with the motion of the boat itself, right? And so what we would see the boat moving in this kind of fashion if we were standing on the side of the bank right here. Okay, it would be going away from us, but also moving diagonally down towards the other side of the bank. The easy part is calculating the velocity is just direction and magnitude. Obviously, we know that magnitude and direction come from the formulas we've already learned. We'll do the magnitude first since it's most common or easiest to do. That's just your Pythagorean theorem, right? So it's 15 squared plus 7 squared. Work that out, and what did you get?
16.55.
So 16.6 meters per second is what we get for just the direction or the magnitude. That's how fast the boat's actually going to be moving. So because the boat's kind of going in sort of downriver, the river is giving the boat a little bit of a speed boost. The direction, if I look at this and I do tangent inverse, it's going to give me a negative angle because it's going to be technically in the fourth quadrant. So tangent inverse of the y part divided by the x part. What does that give us?
I got 25.
It's going to be, it's really it's negative 25 we'll just say 0.2 degrees. But we're going to characterize that with a direction, right? Like a cardinal direction. It would be south of east. Okay, and so I could have just said negative 25.02 degrees because it's in the fourth quadrant, but I can also do this. It's going to be going, if you go east and go down towards the south, then this is exactly how that would work out. Okay, part B. This one talks about calculate the time it takes the boat to cross. Well, the boat has to go across 400 meters. That boat is traveling, that distance is horizontal, right? So how fast is the boat moving horizontally across the river? See this part right here? It's moving 15 meters per second this way. Even though the boat is moving in a diagonal fashion, it's still going 15 meters per second from left to right. It's still going 7 meters per second down the river. That is, in fact, exactly how it moves. And if I'm curious about how fast it goes or how long it takes to go across, then I only need to know about that particular velocity or speed. So what's the formula for velocity, speed, and distance? What does that go? How does that go? How do you say it? D over V equals T. There's a lot of ways you can write this out. We're wanting time, so this is an appropriate group, right? So 400 divided by 15, that is going to give us 26.67 seconds.
Why did you put the velocity as 15 instead of the magnitude that we found?
Because this is considering not just horizontal transfer. I'm not moving across the river at 16 meters per second. I'm moving diagonally down the river at 16 meters per second. Across the river, I'm moving 15 meters per second this way. Right? I'm going to go down the river, yes, but I'm going only 15 meters per second across. Even though you have separate velocity vectors, I'm still only moving 15 meters per second this way and 7 meters per second south. Since that distance is horizontal, it's straight across, I only care about the velocity in that direction. The same question asks in part C, how far downstream are you going to be when you hit the other side? Right? And so we know that I'm looking for distance now. Then I take velocity times time to get the distance. So how far down the river from where I originally was am I going to be after that amount of time? Well, we know it's 26.67 seconds. How fast are you moving downriver?
16.6 meters per second.
So yeah, no, it's 7 meters per second. Not diagonal distance, not the combination of the two, right? But just in terms of straight down. When you multiply those together, you're going to get 186.67 meters is how far down the river you would end up from where you started. Does that make sense? What's that?
If you found the velocity for it to go at an angle and you're trying to figure out where it's going to end up when you take the path it's actually going to take, it's not going to go just like straight down. It's going to go at an angle.
True.
So why are we using
But the vector, I'm curious on the distance I'm concerned about in terms of if I'm on my paper, if I draw the picture out. It looks like this, right? The boat's traveling in this direction. But even though the boat takes a diagonal path, the boat is still traveling 15 meters per second across the river and 7 meters per second down the river. That's still an actual statement. It's 15.7, 15.7, 15.7. If I were to take that path, I would still end up in the same path if I just took diagonal all the way across. Okay? Because we're talking about, if this is where I started from, that's zero distance. When I get here to this position, when I hit the other side of the bank, I'm curious on how far that is, right? It took me 26.7 seconds to do that. I traveled 7 meters per second this way. Since that distance is parallel to that side, and that velocity is in that direction, then you have to keep those two things matched up.
So pretty much for all these problems, you're not going to use.
Not unless it's talking about going in a diagonal, right? The river is going up and down. And so you wouldn't really use that part. True. Okay, so here's the next question. This is the part that we haven't really gotten to. This is not complicated, but if you hadn't done it, it'd be kind of weird to do it by yourself for the first time. If the boat, if I want to end up horizontally across the river from right where I start, the boat's going to have to turn an angle, and it's going to have to go upstream a little bit. So that it goes upstream, so that it's really kind of going across this way, and it ends up going directly across the stream. So I'm going to have to turn the boat into the river, like upstream, to end up. So if I want this to be my resultant vector, going straight across, then I'm going to have to turn the boat up just a little bit. I'm going to head this way, right? I'm still traveling at 15 meters per second, and the water is still going at 7 meters per second. Then the question is, what angle do I have to turn into the river upstream to keep it going? Can you find the angle of this triangle? How?
Hypotenuse over opposite over hypotenuse.
I need sine. Okay? It's going to be sine theta is equal to the opposite over the hypotenuse. When I do that, that's going to get me
27.8.
That's going to be north of east. Right? That's the traditional angle position. Right? So if the boat turns 27.8 degrees and heads that way, the river will push the boat back down just enough to make the boat look like, if I'm standing on the side of the river, the boat's going to be angled, and it's going to be thinking, it's going to be trying to go upstream, but because of the river, the boat's just going to go, it's going to be kind of angled, but it's going to go right across the river like it's horizontal, but it's going to be turned. Okay? And so that's how you do that kind of question. You can try number 6. When you try these questions, a visual image is always a really good idea. At least for me, that's something I always try to do. I'm a very visual learner, right? So I like to put them together. The plane is trying to fly due north, right? However, there's a wind blowing from the east at 30 miles an hour, or 30 meters per second. Which, when it says from the west, which direction is it actually going? It's actually going east, right? It's flowing just the opposite of where it comes from. So we know that the picture looks like this. You have 100 meters per second here, and then you have 30 meters per second here. So the plane's really flying kind of like this, if it doesn't correct its course. That's where they're trying to go. That's great, but this plane's trying to go due north. That's not happening here, right? What's the actual heading, or what's the plane's velocity? But remember, velocity means magnitude and direction. So I've got to give both of those things to start with. And so here we would say, we'll call this just v. We'd say the magnitude of v is equal to 30 squared plus 100 squared, and we'd square root that. So, okay, it's 104.4 meters per second. What about the angle measure? Tan inverse of the y part, that's going to be 100 over the 30. Point what? So 73.3 degrees. Now, that angle really would be the angle right here. Okay, so if you set that angle, then you would say this would be north of east. I could also turn that around and talk about what's the other side of that. All right, and that would be what? 16.7 degrees, right? You could say it's 16.7 degrees east of north, right? That would be this particular angle. So either one of those would essentially get you the right direction. The reason we talk about this one from north, in traditional bearing descriptions, you usually go from north, right? 0 degrees happens to be north in terms of bearings, so that's pretty common. All right, that's part A. Part B says, what heading and direction should the plane take in order to head due north in spite of the wind? So part B, this is kind of like what we did in part D in the previous question. If the result I want, if that's the actual wind plus the plane, then what do I do if the plane flies this direction and the wind is still pushing me back this direction? The plane's still at 100 meters per second, and that's still at 30 meters per second. What angle does the plane need to turn into in order to make that happen? This is where I look at a triangle. I've got a right triangle. So we're going to just say sine of theta is equal to 30 over 100. And that turns out to give me, what is it, 17.5, right? 17.5 degrees. Now I have to be very careful about this. 17.5 is not the correct answer in terms of just plain angle measures, because that's assuming that it's at the origin. I really need to characterize this in terms of like cardinal directions. So that's actually west of north, right? If I wanted to give the true angle measure, I would add 90 to that number, right? Because if I treat this like it's at the origin, this part is 90 plus the little extra bit over here. So it also asks me for, is it the speed next? Right? How fast would the plane be flying in the northerly direction in the part you found in part B, right? So part C asks for speed or velocity. I guess speed part of velocity. And so we're going to end up going 100 squared equals 30 squared plus x squared. So we're going to get x being equal to the square root of 100 squared minus 30 squared, which is like 95.4 meters per second. Okay, any questions about that? Okay, the last part, part D, it's asking, okay, how long is it going to take the plane to get to a destination that's 30 kilometers due north? Be careful. I want to go north, and I want to go 30 kilometers. I know how fast I'm traveling, 95.4 meters per second. How long would it take me to go 30 kilometers if I'm traveling 95.4 meters per second? I'm going to have to change my kilometers or kilometers, however you want to say it, into meters. So if you have 30 kilometers, then how many meters is that? That's 30,000 meters, right? 1 kilometer is equal to 1,000 meters. So I need to make sure to change that over. I also know that if I know how fast I'm traveling, or if I'm doing distance, right? Distance divided by velocity equals time, right? So I know how far it's going to be. I know that I'm traveling at 95.4 meters per second. Divide those two things together, and you're going to get essentially 314.5 seconds. Let's go over number 7 real quick.
I did
Okay.
over velocity.
So first of all, I need to find my velocity. So I know that the plane is traveling due east at 150 meters per second.
Oh, wait.
Guess what? The plane is being pushed along by a 50 meter per second wind. So if I were to think about this, this is the vector 150, 0, plus the vector 50, 0. That would give me a total vector of 200, 0, due east. Okay? And so how much time will it take the plane to travel across 200 kilometers? Well, we know that 200 kilometers is equal to 200,000 meters. And so I know that I'm traveling. I could do the Pythagorean theorem here, but that's kind of pointless. 200 meters per second is how fast the plane is moving with the boost of the wind directly behind it. And so we would simply say distance divided by velocity is equal to the time.
I got 1,000.
So 200,000 divided by 200 meters per second tells us that it's going to take 1,000 seconds for this plane to transverse that 200 kilometers. Okay? Change that idea just a little bit and come up with the idea that you're going in the opposite direction. Still traveling at 150 meters per second. That's the speed of the plane. But now you're also going to be traveling against a wind, right, that's backwards, still at 50 meters per second. So if we think about that one, this is still 50, 0. But now it's negative 150, 0. Because I'm moving left to the negative side of the x-axis, right? So you're going negative 100, 0 in terms of my vector. So I am moving backwards directly into the wind. So it's now going to reduce my speed by 50. So the plane would be traveling at 100 meters per second. I'm going twice as slow, right? So it should take me twice as long to travel. So I can do the same thing again. 200,000 divided by 100. That's going to take me 2,000 seconds. Number 8 is one. I'm not even going to draw this one. You can draw it. You can get kind of this pack. It's not a triangle. It's probably more like a quadrilateral. But if we write it out just in vector form, it's pretty straightforward. A very lost goose flies 30 kilometers north, right? That's straight up. So that's 0, 30. Then 50 kilometers east, that's going to be, east would be x-axis, 0, or 50, 0. Then 70 kilometers south. So that's going to be 0, negative 70. if I have all the vectors components like this, if I want to know where the goose is at this moment, if I were to go from the very beginning to the final destination, we just add them all together. So the sum of all those vectors would look like this: 50, negative 40. And it says, where is it relative to its starting position? I'm going to have to give it a magnitude and a direction, not just the components. So we'd say the actual angle would be your tangent inverse of your negative 40 over 50. And that would give you 50, well, it'd give you negative 38.66 degrees, but we're going to call that 38.66 degrees south of east. You could also talk about that being, I guess, 51.34 degrees east of south. I really probably would go with the first answer there, although it doesn't really matter. The magnitude of the vector is going to be equal to 50 squared plus negative 40 squared. That would give you 64.03 kilometers.
I have a question.
Yep.
Why would it also be 51.34?
So if you draw the picture out, the angle looks like this, right? I could talk about it in that angle. That's the 38.66 degrees. The other side of that, if I go back this way, that would be the 51.34 east on the east side of west, right? So either way, I don't know if there's a real preferred way or not, but that's how you kind of get through that. All right, you can try the rest of these just for practice. I would definitely try some of those longer ones by myself. Check my work at the end. If you get this down, I think you got some of the hardest parts of the vectors chapter. So.